When you hear big boy, you're talking about over 1 million pounds of American steel designed to conquer mountains that broke lesser machines. The Union Pacific big boy locomotives weren't just big, they were engineering marvels that redefined what steam power could do. Built by the American Locomotive Company between 1941 and 1944, these 25 giants hauled freight through the Wasatch Mountains when the nation needed them most. Let's dive into what made them legendary. 10. The articulated frame. The big boy's articulated design was pure genius wrapped in steel. Unlike rigid locomotives that struggled with tight curves, the big boy featured a hinged frame between its front and rear engine sections. This pivot point used a tongue and groove connection that allowed the front set of drivers to swing independently from the rear, all while sharing a single massive boiler mounted to the rear frame. This design came straight from Swiss engineer Anatole Mallet's pioneering work on articulated steam power. This engineering solution tackled an impossible problem. At 132 feet long, a rigid big boy would have torn itself apart trying to navigate mountain curves. But with articulation, these behemoths could handle curves as sharp as 20 degrees without derailing or binding. The front four-wheel pilot truck guided the locomotive into the curve, then the first set of 8 drivers pivoted to follow, while the rear 8 drivers and four-wheel trailing truck maintained their alignment under the cab and firebox. Otto Jabelman and his team engineered this specifically for the tortuous route through Utah's Wasatch Range, where the main line twisted through canyons and around mountainsides on a ruling grade of 1.14%. This wasn't just clever engineering, it was the difference between using 1 locomotive or 3 to move freight across America's backbone. 9. The 300 pounds per square inch boiler pressure. Inside every big boy beat a heart of superheated fury running at 300 pounds per square inch. That boiler pressure represented the absolute cutting edge of 1940s steam technology, pushing the boundaries of what metallurgy could safely contain. The boiler itself stretched 45 feet long and was built from 3 courses of cold-rolled, stress-relieved steel. The front course measured 97 and 11/16 inches in outside diameter with walls 1 and 11/32 inches thick. By the time you reached the third course near the firebox, the diameter had expanded to 106 and 9/16 inches with walls 1 and 3/8 inches thick. This pressure vessel held 10,500 gallons of water, enough to fill a swimming pool 14 feet wide by 28 feet long by 3.5 feet deep. When that water turned to steam at 300 pounds per square inch and over 420 degrees Fahrenheit, saturated steam collected in a dome atop the boiler. But the design didn't stop there. The steam then flowed through superheater elements that snaked back through the flues for over a mile of tubing, converting wet steam into dry, superheated steam that could push pistons with devastating force. The first series featured a Type E superheater with 2,466 square feet of surface area. Managing this kind of pressure required experienced crews. The backhead in the cab was covered with valves and gauges that made operating these locomotives considerably more complex than earlier designs, but that complexity delivered the raw power needed to conquer mountain passes. Before we move on to the next one in the list, I'd like to ask you a small favor. If you're enjoying this content so far, please take a second to like this video and subscribe to the channel. Over 98% of you watch these videos without subscribing. Imagine what we could accomplish if everyone subscribed. It costs you nothing, but it makes a huge difference to us. Thanks to all of you who do. 8. The massive firebox. The firebox of a big boy was a cathedral of combustion measuring 235 inches long by 96 inches wide, with a grate area of approximately 150 square feet. This wasn't just big for the sake of being big. Union Pacific needed this size to burn the low-quality bituminous coal coming from their Wyoming mines. Poor coal meant more of it burning simultaneously to generate the heat required for 300 pounds per square inch steam production. The firebox design came directly from enlarging the Challenger locomotive's firebox, which Union Pacific and ALCO engineers determined was the key to achieving their power goals. Inside this combustion chamber, 75 fire tubes measuring 2.25 inches in diameter and an additional 184 4-inch fire tubes, all about 22 feet long, carried hot gases through the boiler to turn water into steam. These tubes provided 5,889 square feet of evaporative surface area in the first series. The firebox sat on the rear frame, supported by a 4-wheel trailing truck designed specifically to handle its weight and the weight of the cab. Heat from burning coal radiated through the firebox walls and tubes, boiling the surrounding water into the steam that powered everything. The sheer volume of fuel this setup could process was staggering. The firebox was designed to consume coal continuously at rates exceeding 12 tons per hour when operating at full throttle. That's 25,000 pounds of coal disappearing into flames every 60 minutes, creating an inferno that generated the heat needed to keep that enormous boiler producing steam. Without this combustion chamber, the big boy would have been just another underpowered locomotive struggling on mountain grades. 7. The standard stoker system. Hand-firing 12 tons of coal per hour into a firebox was physically impossible, which is why every big boy came equipped with a standard Stoker Company Type MB automatic stoker. This mechanical marvel used an auger that looked like a giant corkscrew to carry lumps of coal from the tender through a conduit running under the cab and up to a trough just below the firebox doors. The stoker motor could feed over 12.5 tons per hour into the firebox, matching the locomotive's appetite for fuel. But feeding coal to the firebox was only half the challenge. The stoker system used steam jets to distribute coal throughout the firebox's 150 square feet of grate area. 7 individual jets, each controlled by its own valve, hurled coal toward different zones to maintain an even firebed. The jets connected to a manifold that required about 100 to 150 pounds of pressure to operate properly. Too little pressure and the coal accumulated at the back. Too much pressure and it piled up at the front. The firemen constantly adjusted the stoker intermediate jet valve to maintain proper pressure as boiler conditions changed. This system represented sophisticated automation for its era. The firemen still monitored the fire and adjusted settings, but the brutal physical labor of shoveling 25,000 pounds of coal per hour was eliminated. The stoker made it possible for 2 men to operate a locomotive that produced over 6,000 horsepower. Without this technology, the firebox would have been unusable. The stoker turned what could have been the design's greatest weakness into one of its most efficient features, ensuring consistent steam production regardless of how hard the engine was working. 6. The 16 driving wheels. The Big Boy's 4-8-8-4 wheel arrangement was unique in railroad history. No other locomotive ever used this configuration. Those numbers tell the whole story. 4 pilot wheels up front, 2 sets of 8 driving wheels in the middle, and 4 trailing wheels under the cab. Each driving wheel measured 68 inches in diameter, chosen specifically because Union Pacific and Alco engineers had reduced the wheel size from the Challenger's 69-inch drivers. Smaller wheels meant more torque at lower speeds, perfect for grinding up mountain grades. 16 drivers meant something critical: weight distribution for traction. Union Pacific's design team calculated they needed 135,000 pounds of tractive effort to haul 3,600 tons up the 1.14% grade of the Wasatch subdivision, with a factor of adhesion of 4.0 that required 540,000 pounds on the drivers. At 67,800 pounds per axle, you needed 8 axles. Each set of 8 drivers was powered by a single massive piston on each side of the locomotive. The cylinders measured 23 3/4 inches in diameter with a 32-inch stroke. Steam from that 300 pounds per square inch boiler pushed those pistons back and forth, turning the driving wheels that moved the entire machine. The multiplication of power was the game changer. 2 complete engines under one boiler, each with its own set of 8 drivers, meant putting more power to the rails than any single engine design could achieve. The articulated frame kept all 16 drivers in contact with the track through curves that would have lifted the wheels of a rigid locomotive. Those drivers could generate 135,375 pounds of starting tractive effort, enough to get a mile-long freight train moving from a standstill on a mountain grade. In motion, the Big Boys generated over 6,290 drawbar horsepower at 41 miles per hour during tests. 5. The colossal weight. When you stepped onto the scales with a big boy, the numbers were staggering. The locomotive alone weighed 772,250 pounds empty. Add the tender at 436,500 pounds, and you had 1,208,750 pounds of machinery, or just over 600 tons. To put this in perspective, a fully loaded big boy outweighed a Boeing 747 jumbo jet. This made them the heaviest reciprocating steam locomotives ever built. There was speculation that Chesapeake and Ohio's Allegheny locomotives might have weighed more, but careful reweighing proved the big boys held the crown. Every pound served a purpose. The weight provided the downward force needed to convert 135,000 pounds of tractive effort into actual movement without spinning the drivers. The boiler full of water added 87,150 pounds alone, since 10,500 gallons at 8.3 pounds per gallon made for over 43 tons of liquid. The massive firebox, the thick boiler plates capable of containing 300 pounds per square inch, the 2 sets of cylinders and valve gear, the articulated frame, all that steel added up quickly. But weight came with consequences. Track had to be maintained to higher standards where big boys operated. Bridges required inspection and sometimes reinforcement. Axle loading was carefully calculated at 67,800 pounds to avoid damaging roadbed, which limited where these giants could travel. Curves had to be negotiated carefully despite the articulated design. The sheer momentum of 600 tons moving at speed meant stopping distances measured in thousands of feet. Union Pacific equipped big boys with dual air pump systems to ensure the brakes could handle this massive machine. When a big boy was on the move, everything else got out of the way or got crushed. 4. The massive water consumption. A big boy's thirst was legendary. The tender on the first 20 locomotives carried 24,000 gallons of water. The final 5, built in 1944, had capacity increased to 25,000 gallons. That sounds like plenty until you realize what happened to that water. At full throttle, a big boy consumed approximately 12,000 gallons per hour. That meant even with a full tender, you had roughly 2 hours of running time before needing to stop for water. The water was pumped into the boiler by 2 injector systems. On the right side, a Nathan-type 4000C automatic restarting injector could deliver 12,500 gallons per hour. On the left, an Alesco TP502 exhaust steam injector rated for 14,050 gallons per hour. These injectors used steam pressure to force water into the boiler against that 300 pounds per square inch internal pressure. The exhaust steam injector was particularly clever, using waste steam from the cylinders to heat the feed water and force it into the boiler, recovering energy that would otherwise be lost. Every gallon that went into the boiler came out as steam through those cylinders, eventually exhausting through the smokestack. This continuous water to steam conversion powered everything. It drove the pistons that turned the wheels. It powered the stoker motor. It operated the injectors. It even provided pressure for the steam jets that distributed coal in the firebox. Towns along the route maintained massive water towers holding hundreds of thousands of gallons. The coaling tower at Cheyenne could hold 650 tons of coal and spanned 4 tracks, supplying multiple locomotives simultaneously. Without water, a big boy was just 600 tons of immobile steel. 3. The mind-blowing hauling capacity. The big boy was officially rated to haul 3,600 tons unassisted up the 1.14% ruling grade between Ogden, Utah, and Green River, Wyoming. That's the equivalent of pulling 50 loaded freight cars up a mountain without helper engines. But in practice, big boys routinely exceeded their ratings. During initial testing in 1941, they demonstrated they could handle 4,200 tons on that same grade at sustained speeds of 18 to 20 miles per hour. A test run on April 2, 1943, saw big boy number 4014 pull 65 freight cars between Ogden and Evanston, generating a maximum of 5,530 horsepower. The tonnage ratings varied depending on the grade. Over Sherman Hill in Wyoming, where the westbound grade hit 1.55%, eastbound tonnage ratings stood at 5,100 tons. On flatter sections of the overland route, where grades were 0.82% or less, big boys could handle trains of roughly 6,000 tons in either direction. The limiting factors became siding length and the locomotive's capacity to recharge the train's air brake system rather than raw pulling power. Crews held these locomotives in high regard, finding them sure-footed and more user-friendly than other motive power of the era. This capacity revolutionized operations. Before the big boys arrived, Union Pacific needed multiple locomotives and helpers to move the same tonnage. The big boy eliminated helper engines on the Wasatch grades, cutting costs and increasing efficiency. These 25 locomotives handled a massive portion of Union Pacific's freight traffic through the mountains during World War II, moving war materials, agricultural products, and commercial freight when America needed it most. A single big boy could do the work of 3 smaller locomotives and do it faster and more reliably. 2. The 80-mile-per-hour design speed. Here's where the big boy got truly impressive. While most freight locomotives were designed for slow, steady pulling, the big boy was engineered to run smoothly and safely at 80 miles per hour. Otto Jabelmann and the Union Pacific design team built in this wide margin of reliability, even though big boys rarely operated above 60 miles per hour in regular freight service. This over-engineering meant the locomotive had structural strength and balance far exceeding what daily operations demanded. The high-speed capability came from careful attention to dynamic forces. The articulated frame had to pivot smoothly at speed without binding or hunting on the rails. The massive counterweights on the driving wheels balanced the reciprocating mass of the pistons and valve gear, reducing hammer blow on the track. The suspension system used equalization between the driving wheels to maintain constant rail contact. The 4-wheel leading truck provided stability entering curves at speed, while the 4-wheel trailing truck kept the rear planted under the heavy firebox and cab. In practice, big boys pulled expedited fruit blocks and time freights over the Wasatch at speeds regularly exceeding 50 miles per hour on level or downgrade sections. The overland route was Union Pacific's primary east-west corridor, and maintaining schedule adherence meant moving fast when terrain permitted. While no big boy ever actually hit that 80 miles per hour design speed in revenue service, knowing they could meant engineers could run them harder without fear of catastrophic failure. That safety margin translated into faster schedules, better on-time performance, and the ability to keep America's freight moving during the most critical years of the mid-20th century. 1. The restoration of number 4014. The most deadly feature of the big boy isn't from the 1940s, it's happening right now. In 2013, Union Pacific reacquired Big Boy number 4014 from the Railway and Locomotive Historical Society in Pomona, California, where it had been on static display since 1962. The decision to restore a big boy to operating condition was unprecedented. Number 4014 had traveled 1,031,205 miles during its career, logging its last revenue run on July 21, 1959, just hours before the final run by any big boy. It was officially retired on December 7, 1961. The restoration took over 6 years and required upgrading the Union Pacific Steam Shop in Cheyenne to accommodate a locomotive of this size. The team converted number 4014 from coal to number 5 fuel oil, solving the problems that plagued an earlier attempt on number 4005 in 1946. That first conversion failed due to uneven heating in the massive firebox with its single burner design. Modern oil-burning technology allowed for proper heat distribution in that 235 by 96-inch firebox. The boiler was recertified to operate at 300 pounds per square inch. Every system was rebuilt or replaced: the stoker mechanism, the injectors, the valve gear, the running gear, the air brake systems. Number 4014 returned to service in May 2019 to celebrate the 150th anniversary of the Transcontinental Railroad's completion. It rolled under its own power for the first time in 60 years, once again holding the title of the world's largest and most powerful operating steam locomotive. Since then, it has made excursion runs across Union Pacific territory, drawing enormous crowds at every stop. The sight of 600 tons thundering down the main line at speed, smoke billowing and whistle screaming, connects people to an era when machines like these shaped the nation. 8 big boys survive in museums, but only number 4014 lives and breathes. That makes it the deadliest feature of all. The Union Pacific big boy locomotives weren't just machines, they were monuments to American engineering excellence built when the country needed them most. From that articulated frame to the restoration of number 4014, every feature represented the absolute peak of steam technology. 25 were built, and though diesel-electric locomotives replaced them by 1962, their legacy thunders on. Hope you found this video helpful. If you're into American machinery that shaped history, hit that subscribe button. We've got more massive machines and forgotten engineering marvels coming your way. Until next time, keep remembering when American industry built things that literally moved mountains.